Welcome to The Explainer. Today, we're going to dive into one of the big ones, a core principle of circuit analysis, Kirchhoff's voltage law, or KVL. Now, this isn't just some formula you have to memorize. It's really the key to understanding the entire energy budget of any closed circuit you're ever going to see.
So let's kick things off with a pretty basic question. You've got a circuit, right? You hook up a battery. Where does all that voltage actually go? It can't just disappear into thin air. Well, KVL gives us this really elegant answer for how every single volt gets accounted for. All right, so here's our game plan. We're going to start with the big idea behind KVL, which is all about energy conservation. Then we'll nail down the official definition, see how to apply it to some simple sources, and then watch how it works with voltage drops in a real-world circuit. And finally, we'll put together the classic KVL equation and talk about why this law is just so powerful. Now, before we jump into any of the math, it's super important to get this one thing. KVL isn't just some random rule somebody made up. At its heart, it's really just the law of conservation of energy, but applied to electric circuits. You know, in physics, this means the electric field is a conservative field, which is a fancy way of saying that the total energy change when you go in a complete circle is always zero. I love this analogy. Just think about an electron starting its journey. The voltage source, that's like a ski lift. It pulls the electron up the mountain, giving it a bunch of potential energy. That's our voltage rise. Then, as it zips through components like resistors, it starts skiing down the mountain, losing that energy. Those are the voltage drops. So by the time it gets all the way back to where it started, all the energy it gained from the lift has been used up. The net change for the whole trip is zero. Simple as that. Okay, so now that we've got that physical picture in our heads, let's look at the formal definition. This is how we translate that energy idea into the language of math. The two key ideas here, the ones you really got to remember, are algebraic sum and closed loop. Algebraic sum just means the signs, the pluses and minuses, are incredibly important. We have to keep track of what's a rise and what's a drop. And a closed loop, well, that's exactly what it sounds like, a complete, unbroken path for the current to flow. Now here's another way to say the exact same thing, and honestly, for a lot of people, this one just clicks better. Think of it like a balanced budget. All the voltage you get from your sources, the rises, has to be spent exactly by all the other components, the drops. It's the same rule, just a different way of looking at it. All right, let's get our hands dirty and see this thing in action in the simplest way possible. Before we even worry about resistors, we can see KVL at work just by looking at how voltage sources, like batteries, act when you connect them in series. Oh, this is perfect. This slide shows that whole algebraic sum idea beautifully. On the left, you see the batteries are helping each other out. We call that series aiding. So their voltages just add right up to 4.5 volts. But on the right, look what happens. We've flipped one of the batteries around. Now it's opposing the others, and its voltage actually subtracts from the total, leaving us with just 1.5 volts. It just goes to show you how critical that polarity is. And of course, this whole idea scales right up. If we hook up three 24-volt sources, all helping each other out, in a series aiding setup, we just add them up and get a grand total of 72 volts. Okay, so sources are one thing, but let's build this out into something a little more practical. We're going to add resistors into the loop, and these are the components that actually use up that energy and create what we call voltage drops. So what we're going to do now is take a totally standard series circuit and just apply KVL to it. And the process is all about using our good old friend Ohm's law to figure out the exact voltage drop across each and every one of those resistors. So to find those individual drops, the first thing we need is the one thing that's the same for every part of a series circuit, the total current. And we find that in two easy steps. First, you just add up all the resistances to get the total resistance, RT. Then you use Ohm's law. Total current is just the source voltage divided by that total resistance. Done. All right, once you've got that magic number, the total current, the rest is actually pretty simple. You just apply Ohm's law again, but this time you do it for each resistor one by one. So the voltage drop across the first resistor, R1, is just that total current times R1's resistance. The drop across R2, same current times R2. And you just keep doing that for every resistor in the loop. And check this out. Here's the payoff. In this example, we've got a 10-volt source, and the individual voltage drops we calculated are 2.5, 5, and another 2.5 volts. And what happens when you add those drops together? You get exactly 10 volts. The total of all the drops is a perfect match for the source. KVL holds true. It works. So that perfect balance we just saw, where the source rise perfectly equals the sum of all the drops? That's not a coincidence. It lets us write one single, really powerful equation that describes what's happening with the voltages in any closed loop. And this is it, the KVL equation in all its glory. So by convention, as we kind of trace our way around the loop, we treat the voltage source as a positive gain, a rise. And then we treat the drops across the resistors as negative. And when you add all of those up, the positive rise and all the negative drops, they have to equal 0. It's the perfectly balanced energy equation for that loop. So here's the bottom line. You just have to be consistent. You pick a direction to walk around the loop, and you stick to it. Every time you cross a component from the minus side to the plus side, that's a voltage rise. You treat it as positive. And every time you go from plus to minus, that's a voltage drop. So it's negative. You add them all up, and I promise you, you will always, always get 0. Okay, so we've defined the law, we've seen how it works, but so what? Why is getting this law down so incredibly important for any engineer? Look, KVL is so much more than just something you memorize for a test. Think of it as a fundamental tool in your engineering toolkit. For now, it lets us solve any series circuit you can think of. But even more importantly, it's the bedrock, the foundation for more advanced stuff like mesh analysis, which you're going to absolutely need to tackle those much more complex multi-loop circuits down the road. And that, of course, leaves us with the next big question. We've seen how perfectly KVL handles any single closed path, but what happens when a circuit isn't so neat and tidy? How in the world do we apply this principle when the current has more than one path to choose from? Well, that is the next step in our journey. All right, welcome to the Explainer. Today, we're going to break down one of the absolute cornerstones of electrical engineering, Kirchhoff's voltage law. It's a great question, right? And the answer, which might surprise you, doesn't actually start with wires and batteries. It starts with something much simpler, a journey. So to really get our heads around this, let's just step away from electronics for a second and start with an analogy that I think we can all picture, a simple hike. Okay, so imagine you go for a hike. You climb up some hills, right? You're gaining elevation, gaining potential energy. Then you head back down, losing all that elevation and energy. Now, if you end up at the exact same spot you started, your net change in elevation is 0. It has to be. The energy you gained going up must equal the energy you lost coming down. It's a fundamental law of physics. Now, here's the cool part. That exact same law of energy conservation applies perfectly to an electric circuit. In this world, our elevation is just voltage. The battery, well, that's like climbing the mountain. It gives a voltage rise. And the other components, like these resistors, they're like coming back down the mountain. They cause a voltage drop. So you see where this is going, right? An electron zipping around a circuit is just like our hiker. By the time it makes the complete round trip and gets back to where it started, the total voltage change has to be 0. The rises have to perfectly cancel out the drops. And this simple but honestly brilliant idea that energy is conserved in a circuit loop was officially written down way back in 1845. The physicist who gave it a name was Gustav Kirchhoff. So Kirchhoff's voltage law, or KVL for short, can be put two different ways, but they mean the same thing. The first way is super intuitive. The sum of all the voltage drops has to equal what the source is putting in. The second way, though, says the algebraic sum of all the voltages in a loop is 0. And that version, as you'll see, is way more powerful, especially when circuits start getting messy. And get this, he figured all this out while he was still a student. It's just an amazing example of how a simple, elegant observation about the physical world becomes a fundamental law that pretty much all of modern circuit analysis is built on. Okay, so enough with the theory. Let's see how we can actually put this law to work. Let's start with a nice, simple circuit. Using that first form of KVL, we know that whatever the battery is supplying has to be used up by the components. So we've got a 10-volt drop here and a 5-volt drop there. You just add them up. Our source voltage has to be 15 volts. See? Simple and direct. Right, but what happens when things aren't so simple? What if you've got multiple batteries or a bunch of crisscrossing paths? That's where we need a really solid step-by-step method. And that is exactly why that algebraic sum is 0 version of KVL is so important. Okay, here's the key. You have to have a consistent system. First, just pick a direction to walk around the loop. Clockwise, counterclockwise, honestly, it doesn't matter as long as you stick with it. Now, as you walk, if you go from a minus to a plus terminal on a source, that's a voltage rise, so we give it a plus sign. If you go across a resistor, that's a voltage drop, so it gets a minus sign. Let's try it out on this circuit. We'll start at the bottom left and go clockwise. First, we hit the 50-volt source, going from minus to plus, so that's a rise, plus 50. Then we hit 3 resistors. Those are always drops, so we subtract them, minus 12, minus 6, and minus our unknown, V3. Then we get to the second source, but look, we're going from plus to minus, so that's another drop, minus 15. And all of that together has to equal 0. And from here on out, it's really just simple math. We've got our equation all set up. We just combine all the numbers we know, and then it's pretty straightforward to solve for that one missing piece, V3. And voila, you do the math, and it turns out the voltage drop across that third resistor has to be exactly 17 volts. It's the only way the numbers can work. It's the only way for energy to be conserved. The books have to balance.
So you might be thinking, okay, that's a neat trick for solving a circuit puzzle, but why does this really matter so much? Well, it all boils down to this. KVL isn't just some random rule somebody made up. It is the law of conservation of energy, just dressed up in electrical terms. Whether you think of it as rises equal drops or the algebraic sum is 0, you're really just saying you can't get something for nothing, and that makes it an absolutely essential tool. And here's the most crucial takeaway. KVL isn't just for homework problems. It's one of the big 3. You've got Ohm's law, Kirchhoff's current law, and this one. Without these 3 tools, modern circuit analysis, it just wouldn't exist.
So think about this for a second. That same simple rule of energy conservation we saw with our hiker, it applies to every single one of the millions, maybe billions of tiny closed loops inside the very device you're watching this on right now. From a simple flashlight to a massive supercomputer, energy is always conserved. It's always accounted for. And that really is what Kirchhoff's voltage law is all about.